Alright, we'll continue on with the other examples here, starting off with the Xenon Tetrafluoride. Since it is in word form, it's probably not a bad idea to go ahead and write out the equation for this, or the formula for this. So Xenon Xe tetrafluoride means that we have 4 fluorines. So doing a count of electrons here, Xenon brings 8 electrons, valence electrons. Yes, even though it's not sharing electrons, it does have 8 valence electrons. Plus the fluorine, we have 4 fluorines and it brings 7 each. So that gives us a total of 28 plus 8, which is 36 electrons. So knowing that we have 36 electrons, now we can go ahead and build our structure here. So xenon goes in the middle. Each fluorine goes around. And since fluorine is a group 7A element, we will give it a single bond. And then the 8 electrons around it. So there we have 32 electrons, and 2 more make it 34, and then 2 more make it 36. So we have our 36 electrons here. So there's our correct Lewis structure. Doing the formal charges, we know fluorine has a formal charge of 0 since it has a single bond. And xenon, this is interesting. Let's go ahead and find out what this is. Well, we have 4 electrons that are not being shared, plus we have 1/2 of 2, 4, 6, 8. So that gives us a total of 8 electrons. So the formal charge calculation is 8 valence electrons minus 8 assigned. Hey, we're in good shape here. Okay, so our formal charges are okay. Alrighty, so we have a good Lewis structure here. Let's take a look at the next thing. Okay, so the Vesper shape. So what type of Vesper shape do we have? Well, again, we have 4 external atoms plus 2 lone pairs. So our Vesper shape will be a potential of 6. So again, potential is the number of external atoms plus lone pairs on the central atom. So our potential is 6, which means that if we have 2 lone pairs, we have a square planar shape. Okay, so square planar. Okay, so once we know what the Vesper shape is, now we can determine the hybridization. And again, hybridization, just like with the number of external atoms plus lone pairs, our potential, since we have 4 external atoms and 2 lone pairs, our potential is 6, so we should have D2 sp3 hybridization, or a total of 6 letters, and we do. Sigma and pi bonds. Remember that, or recall that lone pairs of electrons do not share electrons, so we only consider the electrons that are being shared. So we have 4 single bonds. That means we have 4 sigma bonds and no pi bonds. Okay. Indicate whether the compound is polar or not. This is one of our few exceptions here, that if you have a lone pair of electrons, that typically it is a polar compound. However, this structure does form a nice square planar shape where we have a pair of electrons on top and a pair of electrons on the bottom. Since all 4 of these elements lie on the same plane, they cancel each other out in the quote-unquote tug of war, or momentum. Okay, and then these lone pairs don't push or pull, so this is one of our exceptions where we have a nonpolar compound. Okay, so a nonpolar compound. Okay, so we have a nonpolar compound, and we need to know that to help us determine what type of intermolecular forces. The next question that's asked is the type of intramolecular forces. So the forces between the xenon and the fluorine, these two are not sharing these electrons equally at all. Actually, xenon doesn't even have electronegative value, where fluorine has the strongest. So this shared pair of electrons is much, much closer to the fluorine than it is to the xenon. However, it is being shared. So our intramolecular force is polar covalent bonds. and that takes place on all the xenon fluorine single bonds. Again, there are no shared pairs, or there are no intramolecular forces between lone pairs. The type of intermolecular force, this makes this very easy. This is a nonpolar compound, so we only have one choice to choose from: London dispersion. Again, it's a very, very weak force between similar compounds. And then the last thing is the type of solid. Since we do have at least two different types of nonmetals, this falls in the category of a molecular solid when it becomes a solid. Okay, let's go on to the next one here. Alright, oh, another noble gas. How interesting. Alright, so we have sulfur, 2 sulfurs, and each brings 6 electrons. And then we have radon, again, since it's a noble gas, 8 electrons. And then we have 2 fluorines, so 7 electrons and times 2, so 14 plus 8 plus 12, I believe is 34 electrons. Okay, so we're going to be working with 34 electrons in this structure. Let's go ahead and draw our rough Vesper shape here. So we have radon in the middle, fluorine wherever you want it. If you want to put it on opposite sides, that's fine. It doesn't have to go on opposite sides. Sulfur and a sulfur. Now again, let's be smart about our formal charges and how many electrons. We know that all the external atoms get 8, but we know that group 7A metals have single bonds, where group 6A metals have double bonds. So when we finish giving out our electrons to each of these, we have a total of 32 electrons that have been allocated so far. This structure wanted 34 electrons, so we need to put the last pair of electrons on that central atom. Doing formal charge calculations, we have, for our assigned value of electrons, we have 2 plus 1/2 shared, so 2, 4, 6, 8, 10, 12. So 1/2 of 12 gives me a grand total of 8 assigned electrons. And we know that radon has 8 valence electrons, so the the valence minus the assigned gives me a value of 0. So this is our best Lewis dot structure for this compound. And so when determining what shape it is, again, we had 4 external atoms plus 1 lone pair, so that puts us in this category right here with, again, with the 5. Okay, so since we had 1 lone pair, this actually forms a seesaw shape. So we have a seesaw shape here for our compound. And let's see here. Next thing is the hybridization. So the hybridization, we have, again, 4 external atoms plus 1 lone pair, so our potential is 5. So we should have DsP3 hybridization. And we do. Okay. The next thing is the, what is the next thing here? So the next, oops, sorry. So the next thing, click. Come on, baby. Next thing is, we said hybridization was DsP3, sigma and pi. Sigma and pi bonds, we have 4 sigma bonds, because we have 2 single bonds and 2 double bonds, so we have 4 sigma bonds plus 2 pi bonds. So we have, come on. So we have 4 sigma bonds and 2 pi bonds. Again, remember, lone pairs don't share, so we don't have any sigma pi for lone pair. Okay. Indicate whether this compound is polar or not. Again, we have 4 external atoms plus 1 lone pair. This does not fall under the criteria of being a nonpolar compound. Again, the 2 nonpolar compounds would either be linear or square planar. And I believe in our last example we had the square planar, but since this is a seesaw shape, this is very polar. So we have a polar compound. And then the type of intramolecular forces between the sulfur and the radon, different nonmetals, so that's polar covalent. Between the radon and fluorine, again, different types of nonmetals, so that is also polar covalent. Okay, so we have polar covalent bonding. The type of intermolecular forces, it is a polar compound, and we have no hydrogen, so this has to be a dipole-dipole. The type of solid, since we have different non-metals, at least 2 different kinds, this is a molecular solid. Alright, stay tuned for the last example, and I'll make another video for that one.